I use this. I don't switch anything on. I just use it. Is that right?
Yes.
Right. Okay.
Just be able to write.
Okay. Thanks very much. Thank you. Well, good morning. So in this summary here, we're about here. We're just talking about the symmetry groups in particle physics. So there's a very quick run through symmetry and group theory. And that we'll see underlies our description of particle physics. It's interesting that nature seems to accept symmetry and drive the interactions through symmetry. We'll see that symmetry plays an enormous role in physics. So let's start with the simplest kind of group, a rotation group. So there's a whole set of rotations and they have the group properties. If you apply one and then apply another, you get a member of the group. You've got an identity, you've got an inverse rotation. And if we do it in 3 dimensions, they are a function of 3 parameters, 3 angles, the Euler angles. And they perform a continuous group. These things can be varied continuously. Now, under the rotation, the state vector of the system undergoes a transformation to a new state vector, which is given by this operator here on the original state vector. Now, these operations here themselves form the same group structure as the original rotation. So we say they form a representation of the group. Now, if you apply a symmetry operation, and the physics respects the symmetry, then the physics is going to be the same. Any kind of Bra-Ket situation, some probability is not going to be changed. This could be phi, this could be phi prime. These probabilities are going to be the same. So if we replace psi prime by u psi and psi, this bra here, by u dagger with that bra, you can see that this is going to imply immediately that this operation here is unitary. Now the Hamiltonian, the energy operator of the system, is also going to be unchanged. So we're going to get this identity here. And the Hamiltonian being unchanged means that's got to be the same as this, so that it follows from this that UH is equal to 0. So it seems that we've got something that's a conserved quantity, because this is the time development operator here, and it seems to be a constant of the motion. So those are the 2 properties that follow from the symmetry. And you can see that if you differentiate this thing here, if you differentiate this expectation value of this operator, you've got to differentiate both this, and just using the fact that h is the time derivative, and that here, when you take the dagger of this, you're going to get a minus I. You can see that UH minus HU is, and as this commutes, you can see that this thing actually doesn't change. So we've got something, a conserved quantity here. It looks as if we've got a conserved quantum number. But that's not quite true, because for an operator to be observable, we need it to be an emission operator in quantum mechanics. So from this, we've got to get some emission operator if we want to conserve quantum number. Let us take the example of SUN, which is the group of n by n unitary matrices with determinant u equal to +1. UN is just the group of n times n unitary matrices, and this extra property is this S here, this special unitary group, means the determinant of u is +1. Now, as it's a continuous group, you can actually build everything from the neighborhood of doing nothing. This is doing nothing. And so if this is doing nothing here, you can build the whole group properties from just doing some infinitesimal operation from that identity. So you have a rotation, for example, you only need to rotate a very small amount in all the directions to get all the properties of the group, because you can do repeated small operations and you can build up a finite one. So it's only necessary to consider very infinitesimal variations of these parameters, and then we can expand u in this way, just keeping the linear term, and these then are the generators of the group. These generate these little infinitesimal transformations, and we had 3 of them for the rotation group in 3 dimensions. Here we're going to have A of them at the moment. We're going to sum over A. These are the generators. These are the continuously variable parameters, and that I there has been introduced so that these will be Hermitian, because as we know that this u dagger u is equal to 1, here's u dagger, here's u, there's the minus sign coming in, because when you take the dagger, that produces the minus sign here. And you can see from this, if we keep only the linear term, that t is equal to t dagger. So we've got a set of observable generators that are conserved, and so we've got conserved quantum numbers. So it's these things that have got conserved quantum numbers. And of course, as u commutes with the Hamiltonian, so this commutes with the Hamiltonian. Now the fact that the determinant is equal to 1 implies that the trace of these generators is equal to 0. We can see that by just expanding out this determinant and just keeping the top corner, because it'll go through just the same. Along the diagonal you have just this expansion here. Off diagonal you don't have the 1, because remember that the u is 1 plus this I epsilon t. So you have a 1 along here, and then all the other elements have got I epsilon t. Now if you multiply this up and keep just the linear term in this parameter here, you can see that the sum of these things is going to be equal to 0, because this determinant has to be equal to 1. So you've got the trace of all these things is going to, these generators is going to be 0, each generator. Now for SUN, you've got n squared minus 1 generators, of which n minus 1 can be simultaneously diagonalized. Now the number of simultaneously diagonalizable generators is called the rank of the group. So the rank of an SUN group is n minus 1. These are the good quantum numbers. These are the good conserved quantum numbers. Because if they don't commute with each other, they're not any use to be an additive quantum number. So the rank tells us the number of good quantum numbers. For example, for the rotation group, the angular momentum group, we've got 3 generators. N squared minus 1 is 3. It's rank 1 because n minus 1 is 1. So we've got only 1 diagonal generator, T3. I mean, if it's the angular momentum group, we've got Jx, Jy, and Jz, and we normally say Jz is the diagonal one. The rest, Jx doesn't commute with Jz, Jy doesn't commute with Jz. So we've only got 1 conserved quantum number. If we're in SU3, we've got 8 generators, n squared minus 1, and the rank is 2, so we've got 2 conserved quantum numbers, and they're conventionally chosen to be T3 and T8. And the other 6 don't commute with them. So we've got 2 good quantum numbers for SU3. Now if we've got a composite system made of A and B, then when we do this transformation of the system, we've got UA times UB, and then when we expand it out in these infinitesimal rotations, you see that essentially we've got TA plus TB. So these are additive quantum numbers. So these quantum numbers are additive, like Jz is an additive quantum number. So that's the consequence of SUN. Now if we're building up a whole sequence from this infinitesimal one, a finite transformation, we'd build it up this exponential form here. So this would be a finite thing. You can build it up from, here's the identity doing nothing, and just a small epsilon around here. If we wanted to build up one with a a much bigger variation, then you'd find it be in the exponential form, of which, if we were just looking at the infinitesimal, we just keep that. Now, the whole group structure, everything depending on the group, comes from these commutation relations here. This is the TA-TB. TA-TB minus TB-TA is another member of the group, and the coefficient in front of here, this is summing over C, repeated index, we're summing over C, gives you the whole group structure. So everything comes from this so-called Lie algebra. Let's look at a few SUN groups, SU2, SU3, SU5. Now the number of generators, n squared minus 1, is 3, 8, and 24. The rank, which is n minus 1, is 1, 2, and 4. If we look at what the structure constants are, this is just this Levi-Civita symbol, epsilon ABC, where if these are in cyclic order, it's 1. If there's anticyclic, it's minus 1. If any two are the same, it's 0. And that will just give you the commutation relations that you're familiar with. Jx, Jy is equal to I, Jz, or whatever it is, comes just from this structure. Now, what kind of group structure do it? What kind of representations we could have? Well, we could have representations, in this case, of any number of dimensions. This is just the most fundamental one. This is just the doublet. This is, and those are the eigenvalues of T3. Just remember that in the rotation group, this doublet would have T3 equal to plus a half or minus a half if we're doing angular momentum. And so I've just plotted it along the T3 axis. Okay, let's just remember what we're doing there. So if it's the angular momentum group, which is SU2 is, we're plotting the eigenvalues along here of T3. The other generators are the step-up generator and the step-down generator, which we can call T plus and T minus. This is like Tx plus Ity, Tx minus Ity. So those are the three generators. Only one is able to be diagonalized at once, and that's T3, and we've plotted it here. But there are other dimensions of represented, another possibilities. This is a j equals half in angular momentum, j equals 1, j equals 3 halves. So that's a group that we are very familiar with. SU3, what are the dimensions of SU3? Now it turns out that these are the possible representations of SU3. Now that the dimension, representation of dimension, which is the same as the number of generators, is called the adjoint or representation. The one that is the same as the number n here of the SU, whatever group we are, is called the fundamental representation, from which all others can be built. So those are the names of two special representations. Remember, SU3 has got two generators, T3 and T8. So SU3 has got these three. I'm now plotting it in T3 this way and T8 that way. And these are the eigenvalues of these two operators can be simultaneously diagonalized, and so we have that situation there. The other 6 generators are just the step-up and step-down operators connecting these points here. So really, you've got 3 SU2s. You've got an SU2 there, SU2 there, SU2 there. That's the situation. Those are the 8 generators of SU3. 2 are diagonalized, 6 are step-up and step-down operators. Where do these numbers come from? We'll see. We'll use Young Tableau to get those numbers in a minute. Perhaps I should put this one up here. Maybe you're at something like number 20. Okay. Okay, let's use the Young tableau to get these numbers here. Let's do it for SU3. Now, Young tableau, you start off with one box here. This is just the fundamental representation. You put in that box 3. That's one possibility. Supposing you had a representation with 2 boxes, like this. When the boxes go in the horizontal direction, you increase the number from this 3 by 1. When they go in the vertical direction, you decrease the number. Then the dimension of the representation is the product of these numbers times the number of boxes this path goes through. Now this path goes through 2 boxes there and 1 box there. So the dimension of this representation is 12 divided by 2 times 1, which is 6. So this is the 6-dimensional representation. This 6 there. We could have put the box, well, we could have put the box underneath. When we put the box underneath, we decrease the number from 3 in steps of 1. By Hooke's rule, we get the first one going through 2 boxes again, and this one going through 1. This is a dimension 3. It's different from this 3. Notice it's 2 boxes. This is 3 bar. You can sort of see this with SU2. With SU2, you would have had 2 times 3 divided by 2. This would have been 3. So if this had been SU2, this is probably the one that you're most familiar with, this one would have been 3, and this one would have been 1. Let us now consider a composite situation made of 2 triplets and decompose that into the irreducible representation. Irreducible means can't be made any simpler. Now the boxes can be put in, we've got 2 boxes. The 2 boxes can be in this situation or in this situation. So we've already done this decomposition. This was the one which was 6, and this was 3 bar, starting from 3 cross 3. Now let's take something that's relevant for baryons, because this could be 3 colors of baryons. Let's take that and try and decompose that. Well, we've got to add the box to this or add the box to this. So we've got to, first of all, let's take the 6 times 3. So we add the 3rd box. We can either add it to the end, or we can add it down below. It's always sort of concave downwards. You can't have more boxes in the previous row, in the lower row, than the top row. So that's the structure of the thing. So that's 6 times 3. This is coming from 6 times 3, because we just added another box. Let's add another box to this. This box can be added here. Or it could be added below it. So if we work out what this one is, we put always 3 in the first box. Then we put 4, and then we put 5. Then by Hooke's rule, we go through 3 boxes for this one, 2 boxes for this one, and 1 box for this one. So this is a 10-dimensional representation. Here we've got 3, 1 box one number less, one number more, divided by Hooke's rule, which is 3. The other two boxes are 1. So this is an 8. This is also an 8. This one here is 3, 2, 1. This goes through 3 boxes. This goes through 2 boxes. The other one goes through 1 box. So this is a one-dimensional representation. And so as we're doing group theory, it's normal to put the plus sign inside a circle. And so the decomposition we've got is that. Now, you see that there should be 27 possibilities, and the 27 are 10, 8, 8, and 1. So that's the 27. Now, I haven't emphasized something else. If you interchange members in these two things here, this situation will form a symmetric one where they're in line, and this will be antisymmetric under interchange. This will come clearer when we are doing this for real in physics. So this means that this end one here, the singlet, is totally antisymmetric under interchange of any two of these components here. This is totally symmetric. These are mixed symmetry. This is antisymmetric this way and symmetric that way. So this is antisymmetric, mixed, mixed, and symmetric. Now this is the SU2 you're familiar with. That 3 spin-a-half particles will make, if you decompose them, because this could be angular momentum up to 3 halves. Half, half, half. Here is the angular momentum 3 halves. That's totally symmetric. And then we've got 2 doublets here. They're the 8 states when you combine 3 spin-a-half particles. Now here's the exercise for you. Just repeat this for SU6. So decompose 6 times 6 times 6 and see what you get. Now it happens that the ground state baryons lie in the symmetric representation. Why? That won't become clear, but some people here I'm sure know why, because they've done this before. Why do the ground state baryons lie in the symmetric representation? You would have thought that when you interchange 2 quarks, baryons are made of spin-a-half quarks, interchange 2 spin-a-half quarks, you'd have been the antisymmetric representation. Why are they in the symmetric representation? Pardon?
Is it something to do with the lowest angular momentum?
No, with the lowest angular momentum, the ground state, you've got L equals 0. It's not doing anything. It's just it's not. There's no interchange, no symmetry properties added. The lowest angular momentum is symmetric. You're right. If you go up to the first excited state of the baryons with J equals 1, then you would have to worry about the symmetry of angular momentum. Can somebody tell me why? I haven't lectured to you on this yet, but I was just trying to seek, why should the ground state baryons lie in a symmetric one? Okay, this will come clearer. I'm sure you know the reason, but I won't do it now. We'll do it in detail later. But think about it. Okay, what's next? Are there any questions about this? You? Yes?
Explain the Hawk's rule in the books, because I cannot understand that.
So the question is, will I explain this?
Right.
Okay. I am taking, let's be specific. I am taking a system made of 3 triplets, like a baryon, made of 3 quarks. And the quarks could be in the baryon U, D, and S. Okay, so that would be something that we could consider. So we're considering a baryon which could be made, and there's a whole set of baryons. So this could be U, D, and S, U, D, and S for the other quark, U, D, and S. Now you can see I can make 27 different baryons. I can make the proton, which is UUD. I can make the neutron, which is UDD. I can make the lambda, UDS. And I can go down here and I can make 27 different baryons. So when I say the ground state baryons, I mean the whole 27 of them, you know, because the ground state means L equals 0. The lowest state, you know, just like the hydrogen atom, the 1s state, ground state, okay? Right, so out of these 27 baryons, I want to know, on the composite system, the composite baryon is made of one quark here, one quark here, and one quark here. I want to know the symmetries of the baryon, the end product baryon, okay? So I have to decompose this into the irreducible representation. So I've got my 27 states like this, and it turns out that they block diagonalize rather like this. So I've got a 1 here, 8 here, 8 here, and 10 here. So when I do a group rotation, this thing rotates round here, this rotates round here, and there's 0 outside here. It's block diagonal in units, in dimensions of 1, 8, 8, and 10. Okay? It turns out that we're saying that the ground state baryons live in this representation here. It turns, well, I'm going ahead of myself here, but am I explaining your is that the answer that you're looking for or not? No, it isn't. It's not. What?
I have been classes in young so.
I haven't explained why it works. I'm just giving you the end product of the rule. So it just happens that if you're wanting to decompose an SUN group, you can do it in 30 seconds flat, which is a fantastic thing to be able to do. See, so if you're doing SU3, you just add the boxes. Clearly, if you've got 3 boxes, they've got to appear in something. And you write the boxes down so that you always have at least the same number. This has to be greater or equal to the number below. So the possible constructions you have are this. If you're doing 3 things, you have to first do 2 and then add the 3rd box. And the number of possibilities are just this. You always have to have more in the top row or equal to the next row here, you see. So we have only at this stage looked at, well, we've looked at most of these representations. So well, this goes on and on and on, of course. Can you ask another question? I'm not sure whether I'm answering you what you want or not. It's okay, is it? Okay. It is, yeah?
When do you have the 3 bar?
The bar is, it's going to be an anti-quark, You can see that a 3 is a box like that and a 3 bar is this. If I did 3 times 3 bar, I would have a 1 times this situation here, which would equal, I could put the 2 boxes like this, or I could put the 3 boxes under each other. So in this situation, you're going to have 9 states. This will produce 8, I hope, and this will produce 1, because this is 3, 2, 1, and then you've got to use Hooke's rule. So you can sort of see that the 3 and the 3 bar are different. They're both got dimension 3, but one of them, this is antisymmetric in this direction, and this one, of course, is not interchanging anything. So you can see that the structure is different. And it turned out that the 3 bar is the antiparticle. But it's got the same dimension, but it's got different properties. And when you combine 3 with a 3 bar, you actually get a singlet, as well as the octet. This will all become clear when SU3 is everywhere, as you saw from what we did before. Have we actually done it yet? Perhaps we haven't done it yet. Okay, no, we haven't done it yet, so we haven't seen it before. Here is the internal symmetry groups of nature. Now we're talking about what we'll find in nature. We've already mentioned that U1 is QED. We've just mentioned these things. We've got to explain all of this better. That's an additive quantum number charge, and it's built up. You see, we're building up the thing from, this is a kind of finite rotation alpha here. You can expand it out and get 1 plus I epsilon Q. So Q is the generator of U1. The charge operates the generator. Turns out the baryon number and lepton number are also U1s. So the additive baryon number, additive lepton number. This is absolute. It's sacrosanct. It's in QED. Why should these be absolute? We don't know. They look as if they're absolutely true, because we don't see proton decay. We don't see a violation of lepton numbers. This is interesting. There's no reason why they should be absolute. Isospin, which is like like the rotation group, has got 3 generators here. Isospin is only approximately true. If you go to SU3, U, D, and S, you know S is a little bit more massive than U and D. So SU3 of flavor, this is more massive than this. It breaks the symmetry. These don't have the same mass, so this is even more approximate. And if you've got 4 flavors, U, D, S, and charm, SU4 of flavors, even much more approximate. Then we get chiral symmetry. We'll have to explain that. With just a gamma 5 there. This is just listing them. QCD is just this thing, just SU3 of color. We've mentioned that. So these are local. Okay. These are global transformations where the parameters don't depend upon space and time. Then we get local symmetries where the parameters here depend upon space and time. That's much more interesting. These are going to be our gauge theories, and they're going to be absolute. We're looking ahead. We're just giving you a hint. We mentioned that SU5 is a candidate for grand unified theories. Electroweak was the product of these two. So these are the groups that we already have seen in nature. No, we haven't seen them. I'm just listing them here. We've seen some of these groups. Let's talk about finite groups now. Now, finite groups are like parity. When you look in the mirror, you change x to minus x, or particle-antiparticle conjugation, where you change a particle into an antiparticle. These groups have just got 2 elements. If you do it twice, you get back to the original system. So this is doing it once. This is doing nothing. So the group has got 2 elements, the identity doing something. If you do that thing twice, you get back to the original system. So G squared is equal to the identity. So this is a very small group with just 2 group elements. Notice it's not continuous. You can't do a little bit. You have to do the whole thing. It's not a continuous group. It's a finite symmetry group. As before, this still is true. But now when you do it twice in the group representation, it's essentially doing nothing, because it's the identity. This is the representation of that. From these 2 things here, you see that U dagger U dagger is equal to U. So this operation U in this case is already Hermitian. This means that U in this case is already an observable, whereas before we had to do an infinitesimal transformation. Now there is no infinitesimal transformation. So if the eigenvalue of the state is P, whatever the state is, you can see that if you do it twice, P squared is equal to 1, so the allowed eigenvalues are only plus or minus 1. So the parity is either plus or minus. Charge conjugation operators are either plus or minus 1. If you do it on a composite system, on a composite system, then UA, UB acting on this composite system gives multiplicative conserved quantum numbers. So these are now multiplicatively concerned. If we have two systems of parity +1 and -1, combine them together, the combined system has got parity -1. So there's a big distinction between continuous groups, which is this lot, and this lot, which are finite groups. I've listed them here, the ones that we are meeting, time reversal. Now, there is a subtlety here. It doesn't have to be Hermitian. It could be anti-Hermitian or antilinear. I don't want to get involved in that. I put an exercise here, show antilinear. Those that are finding this course a bit boring might try and think about this. So I put a star on that exercise to indicate that this is not something that's crucial to the course. Only those who are a bit bored and want to try something a little mathematical show that time reversal is an antilinear, anti-unitary operator. All the other, well, they're only C and P. They are unitary, and they have got eigenvalues. Okay. Next sheet, right. Thank you. Are there any questions? I think we're going to leave this now. Yes. Are there any questions? We've done symmetry groups. Oh, I say done symmetry groups. We've been scratching the surface of just giving an overview of symmetry groups. Give a flavor for what is going to come later in the year and later in this course. But you can see symmetry, nature loves symmetry. And nature is exploiting symmetry to the full. And that's really quite something. I mean, you can almost bet your boots that if you discover something, you'd better find some symmetry around. That's why supersymmetry is, people feel it's the last symmetry not exploited by nature. It must be true. We haven't got any evidence, any experimental evidence of it, but there are a lot of people believe it's true. Well, we'll come to that. Now, we're going to make everything, we've now done our overview of the overview, and now we're going to be a little bit more pedagogic, not much more pedagogic because we'll run out of time. And we've got to start with the Dirac equation, and we've got people here that have not met it before, so I have got to do it a little bit systematically. We've got to do the Dirac equation because we've got spin-a-half particles. We've got quarks and leptons. They're spin-a-half, so we've got to be absolutely sure we know what we're doing with spin-a-half particles. We've got to do the Dirac equation. I just hope the people are a little bit lost in what I do will seek out the experts in the class here for them to help them through it. Because clearly I have to go rather quickly. Now somebody asked what book I'm following. Well, now I'm following the book Halsane and Martin because that's the one I'm most familiar with. Okay, so Dirac equation. I'm going to start with the Schrödinger equation. This is not so stupid as it looks. So I'm going to talk about a free particle obeys Schrödinger equation. The energy is the kinetic energy, half mv squared, which is just p squared over 2m. In quantum mechanics, the momentum is just the grad operator, I minus I h cross grad. The energy operator is just I h cross d by dt. Has everybody got a sheet, or didn't have enough? Everybody's got a sheet, have they? Good. We're putting h bar equal to 1. So when I put the operator p squared in, I just got to square this thing. I got grad squared, and the energy operator here. There's Schrödinger's equation with a potential 0. Now, and of course, the probability density of finding the system is just, I'm calling it rho, is just the mod squared of the wave function. Now, the thing that we want to do, we want to get the flow of particles, the current. The current is going to be an important thing in particle physics. So I take a finite volume and I consider the flow of particles out of that volume through a little element ds of the surface. Now the number of particles in the volume is this density times dV. So that's the number of particles in this volume V. And I'm considering the flow, and I'm considering the flow out, so I've got minus d by dt. This is the rate of particles leaving this volume. So that's the number leaving. Now I can do it in terms of the flux of the particles flowing in at some distance to some direction to the normal to the surface. And I can integrate over the whole surface here. So this is a surface integral, and this is the flow out is equal to the reduction in the number of particles. So that's just the conservation of particles. This is true in general, not just for Schrödinger's equation. Now, using Gauss's theorem, I can replace the surface integral by the volume integral, where this is now the divergence of this flow. Now you can see I've got two volume integrals, so I can equate for arbitrary volumes, true for arbitrary volumes, I can equate the integrands. So I got d rho dt, and I'll put it over the other side, div j is equal to 0. And that's the continuity equation. This is the probability density, this is the flux density. Now I want to get the flux in terms of the wave function. This is what, and that's what I'm going to do for the Dirac equation. I'm going to do that for Maxwell's equation. I'm going to do that for all quantum equations, but I'll be doing it for the Dirac equation, Schrödinger equation first. So d rho dt, that's just psi star. So if I differentiate that twice, I just get psi star d psi dt plus psi d psi star dt. That's just differentiating that twice. Now I can substitute using Schrödinger's equation here for d psi by dt and d psi star by dt, and I just get this thing, the minus sign coming because of this I here. But when I take the star of this equation, that will of course produce an I there. So that's just using Schrödinger's equation. Now if I want to write this thing in brackets here in terms of a div, which I want to do, notice I can do it this way. So I write that bracket there just as div of this thing. You can see that when I take the div of this, I get 4 terms. 2 of the terms cancel against each other, and the other 2 give me this thing. So this is just follows immediately. Now I've got my expression in terms of the continuity equation, and I can read off the flux, the flow. You can see the flux, oh dear, sorry. The flux is just this thing here. So I've got an expression of the flow of particles in terms of the wave function. That's what I'm after. Here's the probability density in terms of the wave function. Here's the flow of particles. So we can take some solution of this equation. Here's the solution for a free particle. Oh dear. It's not surprising. You see that this is just the momentum dependence, this is just the energy dependence. Not surprising that's a solution. You can just substitute that in and just check. It just gives you back this. So we know this is Schrödinger's equation for a free particle. We just write that down anyway. You can see that if I substitute this thing in here and take the mod squared, I just get n squared, mod n squared. Now for the flow, if I substitute this in here, look, I've got to take the grad of the wave function. When I take the grad, I get an IP dropping down. The I goes that I, give me 1, and I just get P over M. And I get the same here, P over M. So the 2's cancel out, and I just get P over M. Well, that's just the velocity. This is just what you'd expect then. The number of particles going out per unit time is just the velocity. So that's got us sort of familiar with that. That's just Schrödinger's equation. We're doing that because we're going to repeat that for other equations. Let's do relativistic quantum mechanics, which was done first. by Schrödinger, I think. But you can see now you get into problems. Now I'm calling the wave function phi, just to distinguish it from the psi I had before. The energy operator, now I've got two of them, so it's the second derivative time. P squared is just the same as before, grad squared, and I've got an m squared. So that's called the Klein-Gordon equation. Now when I go through the whole system that I had before, by forming this thing, you can see on the right-hand side, you can see that I'm going to get this thing on the right-hand side from what I had before, and I can rewrite that. That's just going to come through the same way. But on the left-hand side now, you can see that I'm now taking the difference of these two equations. So I'm taking this equation here, I'm forming the same kind of thing on this side, and I'm using this equation twice, and I get, this just follows straight from the Klein-Gordon equation. Just taking this minus its complex conjugate, just forming this. You can see that I get that. On the right-hand side, you can see I've got the same thing as I had before, except for the 2m. So this can be identified just as before with the flow of particles. Now using the continuity equation, this thing over here, you can see that I've got to interpret this thing as the probability density. So when I relativize it, again the solution's the same, because if I substitute that in there, I just get back this thing. This is a free particle, so you expect the solution to be there. So the solution's the same form, but the difference is that the flow doesn't have a 2m on the bottom now. So it's still proportional to the velocity, but this is a relativistic situation. But the real problem is this thing here with a 2e in it, because when I substitute that in here and I differentiate with respect to time, I get minus IE dropping down. The minus I goes with the I, give me 1, and it's that gives me the E. This also gives me E, so I've got 2E. Now the probability density depends upon the energy. And this is why this was thrown out immediately. Because it obviously, that's why then Schrödinger went to the non-relativistic version. Amazingly, that described the hydrogen atom, because the hydrogen atom is non-relativistic. Before I discuss that more, let us familiarize ourselves with 4 vectors. Now this is a space-time situation here, so I'm now, when I write a mu on it, that mu goes 0, 1, 2, 3. The 0 component is the time, the 1, 2, 3 is the spatial coordinate. Same with the momentum. Energy is the first component, 3 momenta. So there are 4 vectors. When I take the scalar product of 2 4 vectors, A dot B, just because I've got relativity to worry about, I've got a minus sign between the space-like part of the scalar product and the time-like part. So that's the normal scalar product. This minus coming due to special theory of relativity. So this is the normal scalar product in 3 dimensions, and then when you're in 4 dimensions, you've got that minus sign to worry about. So we get rid of that minus sign in notation by defining another vector with the mu down, the Lorentz index down, and put a minus in front of the space part of the 4 vector. And then when we take the scalar product, if we have 1 index down and 1 up, we then have got just the relationship that we want. So we don't have any minus sign to worry about. Mu just runs over 0, 1, 2, 3, and we can write it like that. So this is just to make sure we get the minus sign correctly. The minus sign is now appearing in this covariant vector. If we want to raise one of these indices, we can just use g mu nu. G mu nu is such that it's diagonal, repeated indices, we have to sum over repeated indices. This thing is diagonal, and the metric we're using is 1, minus 1, minus 1, minus 1. And that just produces the minus sign 3 times in here and the plus sign once. That's the metric we're using. You could have had this minus 1 and the other's 1, but we're using that metric. And we're summing over repeated indices. So we're summing over mu here. We're summing over mu and nu here. So if I take the scalar product of these two things here, p dot x, I'm going to have et minus p dot x. That's the scalar product. Just either from here or from here. If I take p dot p, that's just p squared, that's a 4-vector scalar product, is now if I calculate that, I got e squared minus the 3-vector scalar product. Now if the system is a single particle, we know that that's m squared, because that's e squared equals p squared plus m squared. Remember, c is equal to 1. So p squared is just equal to m squared if p squared is a 4-vector squared, just equal to the mass of the particle if the system is just a particle of mass m. There's one other thing we have to worry about, is the derivative. Now in the derivative, when it's a covariant, the index up, the minus sign now appears in the space-like thing, and when the index down, we've got a plus sign. And you can see why that is so, is because this transforms like this vector here. This transforms like x mu. And x mu, you can see just because it checks, because p mu is a derivative. It's I d mu. So when we take the scalar product of these two, which is d mu, that is just this combination here. It's just going to be like this thing here. And we call that the box square, the D'Alembertian. Sometimes the square is not there, depends what book you're reading in the definition. But that's just the 4-dimensional second derivative. The final thing we need to do, if we're looking at a covariant form of a 4-vector here, this better be a 4-vector on the other side. So you must check all your equations. If you've got a 4-vector on the left-hand side, you've got to have a 4-vector on the right-hand side. So the indices must balance. Those two go away because that's a scalar product. So you've got one up and one down, they go away. You must have on the right-hand side one mu up. You can't have the mu down there. That would be wrong. I'm introducing that with the Klein-Gordon equation because we can go back now and rewrite all this in 4-vector notation. So the first thing is here, what am I doing? Okay, I'm wanting to, I need 3 boards here. Do I? No, I don't. That's better. Yeah. The Klein-Gordon equation, which is this thing, you see the box squared is this derivative. So the Klein-Gordon equation is just this. The minus, I've got to take this over this side. So the Klein-Gordon equation is just that. If I look at the continuity equation, this thing here, you can see I can write that in 4-vector notation. Because now the derivative, you see you've got a 4 derivative, and these two things here form a 4-vector, J mu. So this is the probability flux 4-vector. And the continuity equation is just this. It's just writing this in 4-vector notation. And the current see this current here has formed the 4-vector. You can see I can write that just in this form here. So this has simplified this equation enormously. the solution of the Klein-Gordon equation is this thing. This is just I minus I p dot x, where these are now 4 vectors. And this result here, this is the j mu, can be just written as 2 p mu times n squared. So all of this reduces to that. So clearly we should be, as we've got a relativistic equation with the energy and momentum balancing, this is now t and x, y, z come in the same dimensions. This is a truly relativistic equation. It's that one. Couldn't write Schrödinger's equation in this way, but this is relativistic, so we can. Now let's get back to this problem here. This energy here means that the probability seems to depend upon the energy, depends on what frame you're looking at. So if a particle is going very fast, it seems to have more chance of being at a spot. But this is not as bad as it seems. It's a time-like component of a 4-vector. The probability depends upon the frame you're looking at it. This is okay, since as you boost the system with a velocity v, the volume element contracts just at the rate that the probability density increases. And this keeps the product unchanged. You don't want to have more chance of finding a particle when it's going fast. You don't want to create particles. And so you can see relativity takes care of that. So everything is fine. I mean, this is the Klein-Gordon equation. Everything is fine except for this. This is okay in the probability. This satisfies relativity. But the real problem is that when we substitute it in, the energy, it's not surprising we get back to this result, but the energy is now the square root of this, and the square root of this has a minus possibility. The plus possibility is all right. But now we've got a minus possibility. We've got negative energy solutions. This is serious. Because if your system has got negative energy solutions, the system can keep dropping down to further and further negative energy solutions. The system drops down to its ground state, which is way down, infinitely far below. We're in deep trouble. It's even worse. Negative energy solutions are going to come with a negative probability density. So this is why this equation was thrown out right at the beginning. That's the natural thing to do. Schrödinger knew that he should do this, but he gets nowhere doing this, so he took non-relativistic version of this and was able to get quantum mechanics. That's where quantum mechanics started, with the hydrogen atom and everything. So they threw away this. So this is a real problem. Along comes Dirac. He'd noticed the problem was having a square here. And that gave negative energy solutions with negative probability densities. And he said, well, let us linearize this equation. So we've got energy, momentum, and mass appearing linearly in the equation. That's going to get, he's thinking that's going to solve the problem, or at least it would seem so. But of course, if you linearize this, you don't know what coefficients going in front of these p's, or got coefficients going in front of the mass. So let's just follow our nose and see what we get. What are these coefficients? Should we have a break? Yeah, we should have a break. Okay, could you come back at 10 past? Is that all right? Sorry, are there any questions while I'm on to this at the moment? Obviously, you don't want to ask a question while a break's coming up, so I'll ask immediately you come back. Okay, we'll have a break.
About group theory, the subject the professor was talking yesterday.
Yes.
Where can I get some information, because I never had
Group theory. He's the best person to ask on that.
In a more physics point of view.
Physics point of view. Yeah.
Because we are getting group theory for other lectures.
That's right. Group theory is everywhere. All books, all particle physics books have group theory in them, some more than others. The best thing in group theory is to look at angular momentum and make yourself really familiar with angular momentum, and then draw away from that. But if you see, most of the books are going to be mathematically inclined, and from your question, I think you are wanting a more physical approach to group theory. Is that right? Well, then take angular momentum and really look at angular momentum in terms of what I've been saying. You see, when you have two spin-a-half system, when you have two, let's take a system made of two spin-a-half states. So we're going to say we take a system made of two protons, take two protons with spin-a-half. Now the first proton can be spin up, and the second one can either be also spin up, or it can be spin up, the first one, and the second one spin down. This one can be spin down, that spin up, or they can both be spin down. Okay. If we look at the JZ, which is our T3 operator, okay, in this case it's going to be +1. This case it's going to be 0, 0, -1. Okay. Now we can look at these two here. They're both 0. This one is symmetric. That one is symmetric. We know there's a combination here which is symmetric, so it can be either up, that plus, that up, or it can be antisymmetric. Okay? So, here is the, where is it? No, I haven't done SU2 here. But if we had done 2, if we had done our Lie decomposition, the two states, you've got 4 possibilities here. 3 of them form the symmetric case, and this is forming the antisymmetric case. So here is the 3 that form the symmetric case. So this is the symmetric one, and this is the antisymmetric one. Okay, so you can see that you're already starting to get some feeling for what's going on. So really, you should read particle physics books, the simpler ones, and look at the group theory part. If you're interested in the physics of it, if you're interested in the maths, this thing here would take you quite a bit to justify. And so I'm just stating the answer here because it simplifies everything for us. Okay. But look at any particle physics book. The simpler, the better for the group theory.
Okay.
Okay.
Thank you, Professor.
Good. Getting more and more sophisticated. Yeah, I mean, I better switch this thing off. Pardon? Yeah. Take this off. So are there any questions? Yes? Yes, young tableau. Where do they come? How do they come? So let's take this example here. I've got 3 boxes and I've got to, in principle, form them in all possible ways. And you're asking me what ways can I form them? I can only form them in ways in which the 3 boxes occur such that in a single line there are more or the same number of boxes than in the bottom one. Of course, if I've got 3 to start with, you see the 3 that we were doing. Let's go back a bit on this one. You see the 3 boxes I've drawn red, 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 you see, so, and blue, blue, blue. Really, if I'm going to start with 3 times 3 times 3, I'd better start with just 2 boxes and then add the 3rd box to this situation. Now when I am looking at 2 boxes, the top row must have at least as many in it as any of the subsequent rows. So in this situation, this box, the 2nd box can only be added here or here. There are no other possibilities. You can't think of any other place to add that box. Okay? And then when I come to this situation here, and I add another box to that, it can either go there or there. So those are the 2 possibilities. When I add another box to this, it can either go there or there. There's no, it couldn't go here. Okay? That's the rule. Yep.
How can you decompose a product of representations which have more than 1 box each? For example,
Okay, I see what you mean. Can we have more than 1 box each? Sorry, are you saying can we have 4 boxes?
when we have a product of let's say, the 6 and the 3 bar,
Yes.
how does that work?
6 and 3 bar.
We both have more than 1 box.
Okay. Yep, we're allowed to do that. Let's do 6 and 3 bar. So we're doing a 6. I've unfortunately drawn the 3 bar first. So that's the 3 bar times the 6. Okay. Now, that I can draw as this. Plus this. Hopefully I've got all the possibilities that I can do. Okay, let's see if I get 18 states. I'd better get 18 states. So this is 3, 4, 5, 2. Hooke's rule gives me 4 and 2. So this is a 15. Okay. Plus, this one is 3, 4, 2, 1. This gives me 4, 2. This gives me the 3. Okay, so the 6 3 bar gives me 15 plus 3.
Okay, so you don't have to split them up.
No. No. Yes?
I still cannot understand the numbers from Hooke's rule. As if when we divide within
The Hooke's thing. You don't, the Hooke's thing, yeah. Okay. we take the boxes, increase the number 1 this way, then we divide the answer by the number of boxes the hook goes through. This one goes through 3 boxes. This one goes for each box. This one goes through 2 boxes, this one goes through 1 box. So you take the product of that and divide by the product of that. That's a rule. So you take each box and you do this hook thing here and you count the number of boxes it goes through. It would take me at least a lecture to prove this, and I would have to take a week to understand the lecture before I was giving it. Maybe I would be pushing it. It is so, we're doing an awful lot, but it works. And as SUN, our groups we're going to meet over and over again, this is terrific. If you did get addicted to this, it's dangerous. It's like heroin. You might never leave it because you can do so many powerful things with it. You might forget everything else and get addicted to young tableau because they're really, yes? Sorry, say that again?
When you do the 3 times 3 times 3 on
Yes,
the bottom,
yes.
why are there no bars on the 8? Because they have both got to be there.
Yes, I see what you mean. The bar is different. It's nothing to do with the boxes coming down. It's to do with the fact that this representation is different from a 3. The bar doesn't indicate you're coming down. It just indicates that there's a different representation, 3 bar, than the 3. So the bar doesn't have it wouldn't have a bar on it. There'd be 2 6s if we. Where are we? This way. You see the 6, I can't remember what the 6 bar is. I would guess, if I had to guess it, 6 bar would be this one. Now here's an interesting one. That's an allowed young tableau, okay? So let's do it. Let's just check whether that's 6 bar. 3, 4, 2, 3, okay? That's the, you reduce it 1 down and up this way. So Hooke's rule gives me 3. Hooke's rule gives me 2. Hooke's rule gives me 2 and 1. So 3, 3, 2. That cancels. That gives me a 6. 6 bar. That's 6 bar, okay? And that's 6, okay? And you can sort of see it sort of completes the number down. If you see, if I put that with that, it sort of fills up 3, 2, 1. If I go below that, 4 boxes in a row with SU3, I get nothing because the bottom one is going to be 0. It is happening here. You would think there was one with 3 boxes all the way down here, but it's not, because in SU2 it would be 2, 1, 0, so it doesn't occur. You had a question.
Why isn't just 1 box with a 6 in? Why is that not?
It can be. It can be. Oh, no, sorry. 1 box with a 6 in. 1 box with a 6 in. On its own, you mean? You mean to start with? That's your question.
Yeah, is it not allowed because it's SU3?
Well, it will occur. 6 will occur as the next one here. But yes, this is the first box always has to be in SU3, 3. It's always going to be 3, okay? That's where it starts. For 6, SU6, it'll start with 6 here, 6 here, and 6 here.
So in your exercise at the bottom,
Yes,
that's 6, 6, 6.
that's right. Exactly right.
6 is on their own.
Okay, 6 times, if this was 6, 6, 6, this would be 6, 6, 6, this would be 7, this would be 6, 7, 8. You'd better get, at the end of this, 216 states. You'll do this in 10 seconds. You can do it straight away here. You haven't answered the last part of the question, but that is something that we've got to answer. Any other questions?
So given that question, how do you know you don't start with like the 6, where it's got 2 boxes next to each other? Or do you always have to start with 2 boxes?
You always, in all of your representations that you start with the SUN number here. Okay. This is said to be the most profound paper in the 20th century. Whether that's true or not, I do not. The Dracos equation. It certainly led to a massive change in understanding. You can see at the moment we're linearizing the equation, but we don't know where we got it, because we've got some coefficients. We don't know anything about them. We're just following our nose. We're just, listen, interesting thing to do. You're on the bus. Let's do it. You know, let's see what happens. Okay, well, let's expand it out. Okay, we've got alpha 1, p1, alpha 2, p2. That's just the scalar product here, plus beta m. We've got to do it twice, because we're just e squared. Do it again, times a wave function. Now we've got hundreds of cross terms. We've got 16 to worry about. Out of the 16, 4 of them are alpha 1 squared, p1 squared, or 3 of them are going to be alpha 2, p2 squared. Then we're going to get the cross terms, but we're going to be scrupulous in our order. Alpha 1, alpha 2 here. Sorry. Alpha 1, alpha 2 here. Alpha 2, alpha 1 here. And then we've got beta squared. Now this thing has to be p squared plus m squared. So this has got to be 1. This has got to be 0. And that's got to be 1. So these things that we don't have a clue about, we know quite a bit about them. They all anti-commute with each other. This is an observable, so they're all Hermitian. They all square to 1. So we're following our noses, and we've got quite a lot of information of these A's. Moreover, if we take the trace of any one of them, as we know that they anti-commute, this is the same as having minus b alpha I b, just because they anti-commute. You can take that from here and you can multiply by b, for example, and you'll get this thing here. So we know as they anti-commute, we get a minus sign here. Now when you're taking the trace of 3 things, and clearly they're going to have to be something like matrices, because you can't have a product one way around plus the product the other way around and get 0 unless they're going to be matrices. So you're taking the trace of these matrices. When you take a trace of the matrices, it's unchanged by taking the first one and putting it in the last place. Now beta squared's 1, so that's the trace of alpha I. So this means they're traceless. So we've got matrices that square to 1, which are Hermitian, anti-commute, and traceless. If they're traceless and they're square to 1, they've got to have eigenvalues plus or minus 1. They've got to be even dimension, because the eigenvalues, you know, you've got to make the thing traceless. So along the diagonal, it's got to add up to 0, so you're going to have either plus or minus 1. So they're going to be even dimension. So the traceless Hermitian matrices of even dimension. Let's take the simplest even dimension, 2 by 2. Great. We have got 3 matrices that satisfy that, the Pauli spin matrices. The Pauli spin matrices. Remember the Pauli spin matrices? We've got the diagonal one. We've got, gosh, I can't remember what is the normal notation of these things. Somebody had better help me. I think that's not there. So I've got 3 Pauli spin matrices, whatever they were when you did undergraduate quantum mechanics. We've got 3 of them. Only one can be diagonalized, sigma 3. Only one good eigenvalue. But we haven't got a 4th. The 4th one would have been 1, 1. Would have been, but that's not traceless. So we need to have 4 by 4 matrices. So here's the thing, here's the 4x4 matrices here, and these are the Pauli spin matrices I've written down here, these sigmas. So the first three are, that's clearly traceless, and to make the fourth one traceless, I just put the unit matrix here and minus the unit matrix there, and clearly that's traceless. So this would be the Dirac-Pauli representation. This is one representation. Alternatively, I could have made them traceless by putting the sigma along the diagonal, minus and plus, and this off diagonal. This is another possibility. This is called the Weyl representation. So we've got 4x4 matrices, so that this thing here is a 4-component column vector. This is a 4x4 matrix. It's a 4x4 matrix. This is a 4-component column vector. Let us take this representation and go to very small momenta, so that this term is small in relation to that. In that case, the Dirac equation just becomes the energy beta times the mass. And the 4 solutions now are just beta. 1, 1, minus 1, minus 1. So we've got 2 eigenvalues 1 and 2 eigenvalues minus 1. And so here are the 4 solutions. I've just written them out. The top ones have got the energy equal to m, and the bottom 2 have got the energy equal to minus m. It's going to turn out that these represent a spin-a-half electron and these represent a spin-a-half positron. You can see that suddenly we're trying to get rid of a negative probability density, and suddenly we're talking about spin. Spin has suddenly come in for free. You haven't seen it. You can sort of see it spin because we've got a sigma around. And remember, sigma is the thing that in the rotation group is describing a spin-a-half particle. I'm going a bit ahead here, but you can see suddenly, while we're on top of the bus, we've written this on the back of an envelope, and suddenly we've got the possibility to describe spin. We didn't expect that. We are trying to get rid of a negative probability density. This is fantastic. This doesn't happen in life once in a century, that you try and solve one problem and you solve another one. Now the Dirac equation is this. Let us, as it's relativistic, we can write it in a very posh way now. We know that we can write this in a covariant form. Covariant form means it's the same form in all different Lorentz frames. So here's the energy operator. I'm multiplying through by beta, so there's an extra beta here. Here is the momentum operator, multiplying through by beta. And when I multiply through beta, that term's just m. Now, here I've got I times the derivative, and here's the derivative here. That's just I times d mu downwards. Okay? If you look back, that's what the derivative, that would form this covariant derivative here. Of course, this thing is a scalar, so I'd better form a scalar from this, so let me introduce a gamma mu. The gamma mu is clearly going to have, for the time-like component, beta, and for the space-like components, beta alpha. So this gamma mu is a set of 4x4 matrices, 4x4 matrices. It is not surprising, as these all square to 1, that the gamma mu's essentially, okay, from this and the fact that these anti-commute, it's pretty quick to show that they still anti-commute like this, and they square essentially to 1 up to the metric tensor. Now, if we go through all of that stuff we did here on the continuity equation, and we're going to get the probability density, flux density as a 4 vector, it's not surprising that we're going to have this 4 vector formed in this way. You see, psi bar is the emission conjugate gamma naught. Now the emission conjugate of a column vector is a row vector. So this is a 4 by 4 matrix. This thing here, the structure of this, the structure of that red thing there, psi bar has got 4 components like that. The gamma mu, there are 4 of them. There are 4 by 4 matrices. And then the psi is just this. And this is a single number for each mu, because this is a single number. That's the structure of it. And it turns out that rho is psi dagger psi. Now that's lucky, because that is what Dirac was after. Because psi dagger is the transpose. Well, first of all, let's write psi. This is psi, psi 1, psi 2, psi 3, psi 4. Psi dagger is psi 1 star all the way up to psi 4 star. When I do that product there, I get the mod squared of psi 1 squared all the way up to the mod squared of psi 4 squared. I've got a sums of mod squared. I've satisfied, I have got out, I've solved the problem. I've got a positive definite probability density. Now I was setting this as an exercise. It's not so easy, so let me look at it. Here's the solution. I'll go this through quickly because it's an exercise. Here's the Dirac equation we started with. Let us unfold it in terms of its components. So here's the time-like component, mu is equal to naught. Here is the space-like one, k1, 2, 3, coming from this, and then I've got minus m psi. Now, when we did this, we sort of took the difference. Maybe I can even go back, and it maybe looks better on this one. Remember, we sort of took the difference of 2 equations. Whatever we did, we took the difference of 2 equations. We took the equation minus its emission conjugate. Or we took the equation minus its complex conjugate. But now we're doing matrix stuff. We've got to not just take the complex conjugate, we've got to take the emission conjugate. When we take the emission conjugate of this equation, the I becomes minus I, a dagger goes there, but the matrices have to be inverted when you've got a product of 2 matrices, so it's like this. Similarly here, except that now, when I take the emission conjugate of this, I get a minus sign in there, as well as the dagger on here, and I get a dagger there. Now that minus sign's a pain in the neck, because it now means I cannot form the derivative again like I did here, because I've got the wrong sign. So to remove this pain in the neck, I multiply from the right by psi naught. So psi naught comes in from the right here. And then I say that this product, psi dagger psi naught, is just m psi. I define it in that way. This thing, when it comes through here, removes the minus sign on this one because they anti-commute. So I'm pushing the psi naught through there. They anti-commute so that this thing gives me a psi bar there and gets rid of the minus sign. In this case, when it goes through, this is psi naught squared. So there's no minus sign. So the psi naught gets rid of the pain in the neck at the price of making it a conjugate spinner. That's why you've got this gamma naught in that, and that's why the adjoint equation is this one. Not psi dagger, but psi bar with an extra gamma naught. Now we perform our trick that we did there. We sort of take the Dirac equation, and then we take the complex conjugate equation, and we take the difference. Essentially, we're going to take the sum because we're wanting terms to cancel out. But we've got to construct something like that. So we take the Dirac equation, which is this one, with a psi bar to the left. So we put a psi bar to the left. Then we take this Dirac equation with a psi bar to the right. That's the thing we're constructing. It's sort of following that. And then we get, if we do that, we see that the mass terms cancel, and we get left with this thing here and this thing here. We get left with this and this. And you can see that that will regroup into this. That gives us d mu j mu equal 0. Here's our current. Here is the current. This is the thing we are interested in. This is the current. We've proved that's a current. Satisfies the continuity equation. Therefore, the time-like component of this thing, which is the thing we don't want to be negative, has got a gamma naught there. Now that gamma naught combines with the gamma naught there to give me 1, to give me psi dagger psi, which proves that that's positive. Okay. Now, it's clear that we've already shown that this thing is a 4 vector. It happens to be the 4 current, the 4 probability density. It's got four different numbers describing it. It's a 4 vector. It has got a structure of a number. But there are 4 of them. Mu goes 0, 1, 2, 3, 4, and those 4 numbers form a 4 vector. These are 4 different numbers. Mu, 0, 1, 2, 3, and they form a 4 vector. It's a true vector, so when you do a parity operation, you have its minus on the parity. What other possibilities have we? To sandwich, you see, we're forming different numbers here. In principle, you'd think there's 16 different numbers. We've used 4 of them in a 4 vector. We've got the psi bar here, and we've got the psi here, and we're putting in different matrices here. We've just put in 4 matrices, 0, 1, 2, 3, and we've got a 4 vector. If we put in just the identity in here, 1, 1, 1, 1, we get the scalar. We'd have to prove that's a scalar. And that a scalar is positive under parity. That's just one. We're just using one thing in here, just one. I haven't proved that. We've proved this. We haven't proved that. Let us put the product of 2 gammas in. That would be, then it'd be interesting to see what we get. So we put 2 gammas in. Well, if that was a plus sign there, we know from the problem that we were asked to do here, with a plus sign there, the 4 by 4 nature of these gamma matrices is just the identity. Okay. The Lorentz index is just telling us different gammas. You see, we've got too many spaces going on here. We're talking about the 4 by 4 spaces of the gamma matrices, and they're just the identity, 4 by 4 identity. So that's not going to give us any. If I put the identity in there, I'm just going to get back to this one. So that's nothing new. So the new ones are when there's a minus sign there. And there's 6 different ones with the mu's and u's. So I've got 6 things. So I've got a tensor. I've formed a tensor. We've got 2 Lorentz indexes. So it's got a tensor structure, use 6. Now let me put 3 gamma matrices in. Gamma 1, gamma 2, gamma 3, or something like that. Well, it's better to define something with 4 gamma matrices. Let's define the product of 4 to be gamma 5. That's just going to be a useful notation. So we take the product of 4 with an I in it. And it's easy to show from what we had here for these things that this thing is going to be emission, and it's going to square to 1. And it's going to satisfy, as every one of those appears once, it's going to satisfy this thing being equal to 0. Because for each one of these is going to be in common. Okay. Well, if we're putting 3 in here, we've got all 4 there, and this extra one here is going to be equal to one of the 4. So it's going to actually give us 3 gammas in there. So there are 4 different things that could be in here. So we've got another 4. It turns out that this gamma 5 will have the opposite parity behavior than what it would have had without the gamma 5. So this was a true vector. This has got the opposite parity. This is an axial vector. Remember, a true vector on the parity is a true vector. On the parity goes to minus itself. An axial vector, something like an angular momentum r cross p, both of these change sign on the parity, and so that becomes plus itself. So that's why that parity is opposite to that. When we get down to putting 4 gamma matrices in together, then we're just putting in, you see, if any 2 of these are the same, it will just reduce to this one. So we've got to be 4 different ones here, so that's just gamma 5. And there's only one possibility here, putting 4 in, and so we just get 1. And it's the opposite parity to a scalar, so it's called a pseudoscalar. Let's put 5 in. If we put 5 gamma matrices in here, then 2 of them are going to be the same, square to 1, and we get back to here. So we get nothing new, so that's the end. So out of the possibilities that we can put in here, there's 16 possibilities, and they form that Lorentz type of behavior. These are called bilinear covariants. Let's look at zero mass fermions. Now, in zero mass fermions, here's the Dirac equation that we got on the envelope on the back of a bus, as it were. Here, as the mass is 0, we just cross that out. So we've just got Schrodinger's Dirac equation is just alpha dot p. Now we're just looking for 3 anti-commuting traceless emission matrices. Now we have 3. They're the Pauli matrices. That required us to have 4, and that's why we went up into more dimensions. But if we have a massless particle, we've already done it. It could be minus sigma or plus sigma. They would be equally likely. So what has happened, this one is going to describe a left-handed particle and a right-handed antiparticle. This one's going to be sort of right-handed particle and a left-handed antiparticle. So Dirac's equation, a 4-component equation, has decoupled into 2 different equations. One in which this chi here is these 2. This doublet here is just these 2. Remember that we said that Dirac's equation described the electron with 2 spin states and the positron with 2 spin states. I'm now using it for the neutrino. Here are there are 2 spin states of the neutrino and 2 spin states for the antineutrino. They decouple. They never mix. So it would be possible for nature to select only half. Nature appeared to select this half. This is interesting. So it's got to be massless. And for a long time, it's thought they were massless, but neutrinos have mass, as we'll see later. So this simple picture is going to be a bit clouded. But this is all right. You can see particle physics has got lots of twists in it. This is this puzzle, why nature is selecting only half. When you look in the mirror, there's nothing there, as it were. More sheets. I've obviously got a very tight number of sheets here, so I've got to get it right. Probably wrong. Has everybody got a sheet?
Yeah.
You got a sheet, have you? Yeah. Right. And there are no sheets to spare, is that right? Okay. Can I have that one back? Because it gets a bit precious after a while. Okay. Now, you see, with a zero mass case, we had that as the solution for alpha. If we wanted to find what beta was in this situation, we're now in this representation here. We're in the vial representation. This is very useful at low energies. Momentum much less than the mass. This is a very good representation if the mass is zero. So these two representations are at the opposite end of the spectrum. So it's clear that we should use the vial representation. And then, if we work out what the betas and alphas would be, the gammas would be, they would come to be this. But the interesting one is gamma 5, where it's got gamma, the product of those three. So if you work that out, take that product, it becomes minus I and I, the unit. This is a 2 by 2 matrix, 2 by 2 matrix. Now, if you form, this is the unit matrix minus gamma 5, you can see that that is going to, with that extra minus sign, produce a 1 here when I take into account the half. And this I, when it's 2 by 2 at the bottom, it's going to cancel. So it's projection. This thing here projects out the left-handed chirality. 1 plus gamma 5 projects out the right-handed chirality. Chirality is the handedness of the thing. You can sort of see why that gamma 5 is to do playing around with parity. It's changing the chirality from the bottom two to the top two. Now the electromagnetic current, now you see why current's important, because current is going to be the electron current here coupling to the exchanged photon. The photon is described by the vector potential here, as we will see, carrying a Lorentz index, it's spin 1. The current here is also a 4 vector, and so for electromagnetic interactions you've got left and right coming in. For weak interactions, again with a boson going across here, again with a Lorentz index, it's only coupling to left-handed leptons, and therefore we've got a half 1 minus gamma 5 in it. That projects out always the left-handed chirality. So yes, there's where the 1 minus gamma 5, that is the perverseness of nature that stuck this thing saying only left-handed leptons occur or right-handed antileptons. It's there, that's where it's coming in our basic weak charge current. This is charge because this is W's got a plus, that's a plus charge there. In fact, the W's coming into the electron, that's neutral. What do we do next? Free particle spinners. So we take this Dirac equation, and we operate on this Dirac equation with this operation here. And you can almost see straight away that if I do that, I will get this equation. Because you know that d mu is the box squared. You know that d mu is equal to the box squared. And then you've just got to check that the rest comes in correctly. So that's not a difficult exercise to show that on each component here you have the Klein-Gordon operator. So each component satisfies the Klein-Gordon equation. Now the solution of the Klein-Gordon equation is just e to the minus ip dot x. Remember, just look back. This is a free particle. And we know where this comes from. So the space dependence of the equation we've already got for each component. Each component has got that, but it can have some coefficient with a momentum dependence. And these are called the spinors, the Dirac spinors. So if we substitute this thing into Dirac's equation, and we take the derivative here,